Okay, you're back and you're brave. On with the hardest chapter here. We're gonna move on and talk about integrated rate laws. What does it mean, integrated rate laws? Well, it's when you take the rate law and you integrate it. So again, this is calculus. This is a calculus proof, but it's not a textbook. But this is a calculus-based concept. So if you had calculus, you're at a bit of an advantage here. But without calculus, it's okay. So the first order rate, this is just rate law. Rate is equal to some k to some k concentration of A. It's first order, the first power. And that is rate of disappearance of A minus delta A over delta T. So then you uh, you set these equal to each other and you go to infinitesimal dt, and then you rearrange where you have minus k dt equals dA over A, and you integrate from 0 to t for a time, and A0 to AT. A0, so you can sometimes when you say A0, sometimes you hear it A naught. That's kind of British for zero, all for naught, all for zero. So at the initial time to some time t, and then this is just the constant for the dt, and for inverse the dx over x. This is the natural log, and then we have this equate. Then you can do this way: minus kt is ln a plus minus ln a 0, or you can rearrange it to have your ln of concentration at time t equals minus kt plus natural log of the initial concentration. And this is just like the equation of the line, the y equals mx plus b, like so. Okay, so one of the ways that you can figure out the rate constant of something that's first order is you can graph it. And if you graph the natural log of the concentration versus time, the slope is the opposite of k. So, and you can also get the initial concentration because the ln a0, this is that. So you can get the so e to the 2.3, or e to the minus 2, but that'll tell you the concentration at that time. Okay, so let's do this for an example. The decomposition of SO2Cl2 is first order with that rate constant if the reaction conditions same temperature and the initial concentration is 0.0225 molar. What was the concentration after that much time? So for this one, you just plug in the first order integrated rate law. Here is the first order integrated rate law, and you put it in minus k, so the k is minus 2.9 times 10 to the minus 4, and the units are inverse seconds, times time, 865 seconds, and plus the natural log of the initial concentration. The initial concentration is 0.0225, and you plug this in and you get equals minus 4.04. And then, so this is the natural log of a to the t. So you take e to both sides, and you get concentration of A at some time t is e to the minus 4.04, and just throw that in your handy dandy calculator, and you get 0.0176 molar. Isn't it a lot easier? That's a lot easier to do it that way than doing the other ways, right? So integrated rate laws are great. So I know I mentioned all the stuff with the calculus. You'll be given these equations. So you're given these equations. You just have to know how to use them. So, but I went over the calculus proof just because, hey, you're paying to be in this class, so I should teach you something cool and novel, maybe outside the book. Okay, so why don't you try and do it for this one? Try it on your own. And I've gone ahead and put the answer there so you can try it on your own. Okay, so the second integrated rate law, it's the same thing, except this time you go through all the. I don't necessarily want to go through the derivation for this. It's an interesting one. Instead of because the integral of dx over x squared is minus 1 over x. So your solution here for the second order integrated rate law is 1 over, so the inverse of a times t equals positive kt plus the inverse of the concentration. And so then half-life, this is the time it takes for something to go away, like half of it to go away. And so the for first order, the half-life, here's the derivation right here. The half-life is natural log of 2 over k, or 0.093. That's a natural log of 2 over k. Now, I told you before, most everything is first order. There is something in banking called the rule of 72. That is, if you have an interest rate, if you take 72 divided by that number, that tells you what the how long it'll take for that to double. So for instance, so let's say you have a 3% return on something, and the rule of 72. So 72 divided by 3, so that's going to be 24. So that means if you have $100,000 and you invested in a 3% interest rate rate of return, you will get $200,000. You'll have $200,000 in 24 years. So that's called the law of 72. Where does the law of 72 come from? It comes from, it's close to the law, to the ln of 2. And like I said, interest works in this banks as well. It should really be the rule of 69%. Of course, people think that sounds naughty for one thing. The other thing is that 69 is not a very usable number. It's 3 times 23. So 2 prime numbers that are, it works at 3 is okay, but 23 is a really weird prime number. They picked 72 because it's divisible by 2, 3, 4, 6, and 5, close enough to 5, because that's the reason why they pick the rule of 72. Okay, so so half-life for first order reaction, and I also mentioned nuclear decay works the same way as for first order. So by half-life, it means, like, so if you start at a concentration of 1, if your half-life is 100 seconds, that means your concentration will be 1/2 of what it originally was. After 2 half-lives, it'll be a quarter. 3 half-lives, it'll be 1 over 2 cubed, or 1/8, and so on. In second order, the half-life is 1 over k a naught. So you'll get all these equations, of course. So for instance here, molecular iodine dissociates at that temperature with a first order rate constant of 0.271. What is the half-life of this reaction? It's just a natural log of 2 over the rate constant. So the half-life is natural log of 2 over the rate constant, 0.271 inverse seconds. So that's 2.56 seconds. So it's a very short half-life. Okay, so here is the overview of the integrated rate law. So you can see here for zero order, I didn't really cover zero order, but the integrated rate law is just the time, the concentration of time is equal to minus kT plus the initial concentration. Because remember that the rate is independent of the concentration for A. And there's the straight line plot. It's concentration versus time, and it's this downward plot. And the half-life is just 1 over 2, just initial concentration over 2K. And the first order, like most everything is first order, so this is something you'll probably use in future classes, and certainly the concept, and even no matter what you do in life, you will probably work with bank interest, which is first order. Okay, but the integrated rate law is natural log of concentration time t is equal to minus kt plus the natural log of the initial concentration. And plotting natural log of concentration versus time gives you a negative slope. And then for second order, the rate law is inverse of concentration equals kT plus the inverse of the initial concentration, gives you a positive slope. So if you plot inverse of concentration versus time, you get a positive slope. And this is another way that you can figure out reaction order. So I mentioned last class that you could do data and that kind of thing. And this another way you can do it is you can graph it. So if you graph it, you can determine what the order is by which one gives you a linear relationship. So it's kind of interesting. Okay, and I guess I'm done right now.